All right, so how's everyone doing? Awesome. Any questions? Got PA2 mostly done? Under control at least? Any worries about today's ODP? Shouldn't be too bad. Okay, cool. Yeah, so ODP 209, you're deleting the middle node of 3, but your list does not have a sentinel node. So it's just one node, points to a second, points to a third. You just want to delete that second node. You don't know what the value is in there, so it's not just your general delete function. Okay, you just want to manipulate the pointers manually to remove that node so the first node points to the third and the second is removed. It doesn't care if you free the memory for that second node or not. It's up to you. Yeah, I made sure it didn't crash if you free it. You would?
I didn't free the node.
That's okay. You didn't allocate it, so you shouldn't have to free it, right? All right, so no questions? All right, so we're talking about stacks and queues this week. So probably a couple of days on stacks, a couple of days on queues. And I did a kind of like motivation for an idea of a stack last week, right? The plate of dishes that you take from the top and you put back on the top and so on. That's the model we can kind of work with. Let me start by talking about why we care about stacks. And then we'll move into looking at how we can implement stacks a variety of ways. We can do it basically with an array, we can do it with a linked list, we could do it with other structures as well. But the main two we'll talk about are arrays and linked lists. But let's motivate this first. Let's think about why we care about a stack. So remember the basic setup is first in, last out. Or last in, first out. So when you see the word LIFO, it means a stack. The last thing you put in the stack is the first thing you get out of the stack. So we can picture this. I don't know, here's our plate of dishes. So we usually think of push some thing n. We'll probably deal with n being integers, but it could be anything. Push n says add n to the stack. Pop should return the last thing that was pushed. So for example, if I push the number 5, we can think of that as sitting here on our stack. And if I push -10, that sits on top of it. And if I push -5, that goes right here. And maybe I'll push another 5. And then I can say pop, and that should return that last thing I pushed, which was a 5, and then it gets removed from the stack. And now if I say push 7, that goes onto the stack. I would draw it here if I could erase, but I'll leave the 5 there. So now 7 is the last thing that's been pushed. If I say pop, 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 I'm going to get 7, then -5, then -10, then 5. Right? So first pop returns 7, next returns -5, next returns -10, and these are removed from the stack. And now if I say push 13, that 13 goes on the stack. So now my stack has two things. First is a 5 and then a 13. The 13 will get popped off first and then the 5. And most of how we're interacting with a stack is through this pair of routines, push and pop. Add something to the stack, remove from the stack. We probably want a way to initialize a stack. So we'd have some kind of a init routine that does something to create a stack, an empty stack. So it might allocate memory, it might set up some pointers, it might do any of a number of things, but we want some way to initialize. And when we're dealing with our stack, right, if we push too many things, eventually we're going to run out of storage space. And so we'd like to know if the stack is full. So that before we push something onto the stack, we know if we've got space for it. And we'd also like to know if the stack is empty, so that we don't try to pop something from a stack that doesn't have anything to pop. And this isn't sacred, but for the sake of argument, these 5 routines are really all we need to work with a stack. And so this is getting into the idea of an abstract data type. And we can think of a stack exactly like this. It's a set of routines, a push that saves something onto the stack, a pop that retrieves the last thing that was pushed, and a init that creates an empty stack, and a pair of functions for checking if there's room to push and if there's something to pop. And when we think about stacks from a user perspective, this is what we should be thinking of. When we talk about implementing a stack, we're going to talk about building an array and having something called a stack pointer. And the stack pointer increments after we use it to store something. And it decrements before we pop something and so on. If we talk about implementing a stack with a linked list, we're going to picture a linked list that starts off with a sentinel node. And when you push, you insert right after the sentinel. And when you pop, you remove the node right after the sentinel. And you do your regular insert and delete adjustments of pointers and so on. But all of those details for implementing a stack are completely invisible to the user. So here's the user view of the world, and here's the implementation. So we'll talk a lot about abstract data types this term and next. The basic concept is to describe a data type, a linked list, a stack, a queue, a tree, in terms of how a user interfaces with that data structure, as opposed to in terms of how that data structure is implemented at a low level, using arrays, using struct node pointers, using a variable set to my null, those kinds of details. Those are implementation details. Stack as an abstract data type, right? That's the user view of it. Does that make sense? So for now, I just want to stick to this user view of a stack and talk about why stacks are interesting and useful. Well, here's one example. So suppose you're doing your homework. Working on your physics homework. And while you're in the middle of a problem, you get a message on your phone. So let's say you get a message. And what do? You stop doing your homework and you pick up your phone and you read the message. And it's from a friend saying, you got to check this out. Meet me outside. So you stop reading your text message and you go outside. And there's your friend with a new car. They're like, I just got a new car. Let's go check it out. So now you get in the car and you're done going outside and you go for a drive. And you drive around and you get hungry. So you stop and you get food. All right, you're building up a stack of events, right? You started off by doing your homework. You haven't forgotten about your homework. You're going to get back to it later, hopefully. But right now you're getting food. That's the top of your stack, even though it's on the bottom of the page. That's the top of the stack. And when you're done getting food, you're going to pop this off, and what are you going to do? You're going to go back to driving. And when you're done driving, your friend drops you off, you're at this point where you went outside your door. And now you realize you never got the mail, so you say, let's get the mail. So you put that on top of your stack, and you go to the mailbox, and you get the mail. And there's a cool looking package in there, so you open the package. And it's got some gizmo that you ordered, so you play with it. You play with whatever you got. And then when you're done, you pop that off your stack. And you're done with opening the package. And you're done with getting the mail. You close the mailbox. And you're back to this point where you'd gone outside. So you're done with that, and you go back inside. And you pick up your phone, because you left it there. And you close out your messaging, and now you're back to doing your homework. Okay? This is the way that a lot of us sort of process daily events, is with a stack-based model. You're doing one thing. When something interrupts you, you remember what you were doing, but you go off and you start doing something else. And if something interrupts that, you're going to remember that and do some third thing. And when you're finished with that third, you'll come back to the previous thing you were doing before you got interrupted. And then you'll come back to the prior thing, and so on. Right? Does that sound familiar? So that's kind of how we process events a lot of times in real life. Well, this is how computers process events also. Right? So interrupts, if you've done 270, interrupts are related to the stack. Every time you get interrupted, you save the current state of things on the stack. You go off and process the interrupt. And if you're processing an interrupt and you get another interrupt, higher priority one, you save your current state on the stack. You deal with that new interrupt. When you're done, you come back, you pop the stack, and you continue with the low priority interrupt. And eventually you come back. And we do a less amusing version of this every time we make calls to functions. So you start off with a main program, and I'll put line numbers on my code. So line 10 does something. Line 20 says call function 1. Line 30 says do something else. Line 40 says call function 2. And line 50 is the end. And function 1, let's say it starts at line 100 and does something, and at line 110 it says call function 2, and then 120 it says return. And function 2, line 200 says, I don't know, do something, and then return. So you're executing your main program, you get to this line 20, it says call function 1. You're going to come over here to line 100 and start executing some code. When you get to 110, it's going to say call function 2, so now you're going to go to location 200 and start executing code. And then you get to a return. Where do you return to? You return to function 1, line 120. And that says return. Where do you return to? You return to line 30. How are you going to remember where you're supposed to return to, though? And you can't just save that return into some magic variable because you might have nested calls. So we use a stack. So when you get to this call, we put 20 on the stack. So let me go back to drawing my stack like this. So we put the next instruction's address on the stack. And we go to function 1, we do line 100. 110 says call function 2. So we save on the stack the next instruction to execute after we return. Function 2, we do 200, we do 210. When we're ready to return, we just pop off this 120. That's the location we jump to. And we remove it from the stack. Here's another return. So we take the 30, pop it off the stack. That's the instruction we go back to. Here's another call to function 2. So we'll push a 50 on the stack. Come down to function 2. When this says return, we pop the 50. And it comes back to the end of our program. So this is how stacks are used to handle function calls and returns. And if our main program were to just say return, this is not C anymore, obviously, because it's got line numbers. If our main program just said return, the operating system would say, okay, let's pop whatever's at the top of the stack, but there's nothing in the stack, right? That's a stack underflow. That would be an error. In C, of course, our main program isn't the beginning of the process. It's actually called from something else. So when our main program returns, we go back to that system code that called it. And the other side of that equation is an infinite call loop. So if function fun says call function fun, what's the system going to do? It's going to take the address of the next instruction, put that on the stack, and then go to function fun. And it says call fun, take the address of the next instruction, put that on the stack, jump to function fun, there's a call statement, take the address of the next instruction. What's going to happen? Eventually your stack's going to overflow. On a Unix system, it's big. Usually, when you set up memory, so first of all, we have virtual memory, which is theoretically limited by the size of your hard drive or the size of your swap file. But usually, there's a beginning of memory where we have code and certain types of data and so on. And then there's a big dead space where memory might theoretically exist but doesn't. And then at the end, these addresses like that have lots of ones on the left side. At the very bottom of memory, those memories exist, those locations. And a lot of times that's where the stack starts, is somewhere down in that memory, and it grows upward to lower memory locations. And so at some point, you'll hit a region in your memory map that doesn't actually exist. And that's where your stack will overflow, but it depends on how your system is implemented. So at least millions of locations and probably a whole lot more. On the other hand, on a PIC processor, you only have 30 locations in your stack. And the 31st doesn't exist. So that's a very small stack, but your code's pretty small on a PIC anyway. So memory on a computer, so physical memory, let's say you've got 16 gig. So it goes from 0 to 16 gig minus 1. Okay, that's 16 billion locations of memory that you can access starting with 0 and so on. But our systems don't really interact with physical memory directly. We interact with usually some kind of virtual memory. And virtual memory might be set up as follows. So 0 through some location doesn't exist. That's why you get a seg fault when you try to read memory location 0. And then some other locations of memory might map to some page in physical memory. And there might be some pages here that are unmapped. And there might be a page here that maps to some other block in memory. And so on. So you have pages, regions of virtual memory that your CPU actually accesses, but they correspond to different locations in physical memory. And it may be that some of these aren't mapped to physical locations, and if you try to access something in that location, you get your seg fault.
So what's the advantage of having memory that is in virtual memory also on the left? That could be on my device, or is it like?
No, it's inside your machine. It's not cloud-based yet. So the advantages are, one, your virtual memory can be bigger than your physical memory. Okay, so you might have 16 gig of physical memory, you could have a terabyte of virtual memory. So your CPU thinks there's a trillion memory locations that it can read and write from with its add and increment instructions. But in fact, only some of those are currently mapped to memory, and some of them are sitting on a disk somewhere. So it lets you expand the memory beyond what your physical memory size is. It also lets you manage access to different sections of memory. So your memory management unit, which controls this mapping, can put protections on certain pages and say, anybody can access this, but you need to be an administrator to access that. And that could be where operating system code is stored, or the memory mapped access to physical devices. And we leave gaps in there partially to break up regions that are different, but also so we can do things like start our stack down here and grow it upward. And by having a region here that's inaccessible, we ensure that our stack doesn't accidentally flow into, operating system code or some other piece of code. And this starts to brush a little bit against Meltdown Inspector. Yeah, so if you do computer architecture, you learn all about memory management, and it's a really cool area. The way that this mapping is done critically influences the performance of your processor and your operating system. On a good system, the hardware mapping and the operating system use of it are designed together so that it's optimized. Each is optimized for the other. It doesn't always happen. All right, so stacks are useful for keeping track of your life. Stacks are useful for managing calls and returns. Stacks are useful for local variables. So if you have some function and inside that function you declare 3 integers a, b, c, these need to point somewhere in memory, right, so that we can store values into these variables. But when your function exits, when it returns, these variables technically don't exist anymore, right? The values are not preserved. If I set a equal to 1 and then I call fun again and I look at a, it's not going to have that 1 in it anymore. It exists only within the context of that function. Well, one way that's implemented is by taking these variables and not just storing them anywhere in memory, but storing them inside the stack. So we here's our stack, and it's growing in this direction. Here's things that were pushed, but at some point, we sort of imagine a fictitious line here, and we say, okay, here's where I'm going to store A, here's where I'm going to store B, here's where I'm going to store C, and I'm going to move the pointers in my stack so that now this is the top of the stack. This is where the next thing will get pushed. And if I do other function calls or things interrupt me or things that affect the stack, right, they start going on the stack from this point up. They don't affect A, B, C. These are now memory locations I can just use to store these local variables. But when I execute my return, what happens? My stack pointer goes back to where it was when I called my function, and all of these locations that I used for variables are now available for general use on the stack. So C in particular uses stack space for local vars, and the space automatically gets reclaimed when your function returns. This also lets us do recursion, because inside here, if the function fun calls itself, what's going to happen? Well, it's going to save the return address. And then, since there's 3 local variables, it's going to set aside space on the stack for those. And then it's going to change the stack pointer, so the top of stack is sitting right here. So the version of fun that was called from fun is using these memory locations for its variables A, B, C. When that returns, right, our stack changes back to here where this is the top of the stack, and now A, B, C refer to these memory locations. So if you have a function that calls itself, the value of local variables is preserved through that call. And when you return from that call, your variables are still intact. And that's going to be a key for doing recursion, which we're coming up to in a couple of weeks. Yeah? Yes. So if you have a static variable, for example, that actually goes into a location in memory that's not on the stack. It goes into some location that the compiler has arranged to not have disturbed. All right, what else can we do with stacks? I'm horrible at drawing mazes, but let's do something like a maze. Suppose I'm sitting at some start point, and I've got 3 ways that I can go. So I'm going to call this point A, and I can follow roads 1, 2, or 3. If I take road 1, I'll eventually come to a point B where I can go one of 2 ways, 1 or 2. If I took road 2, I'll come to a place C where I can go, let's say, one of 2 ways, 1 or 2. And if I took road A, road 3, I'll come to a fork where there's 3 ways I can go. So we'll call that city D, and I could take road 1, 2, or 3. And at this point, maybe I have a pair of options. And at this point, maybe I have a pair of options. And let's say one more. And here's the pot of gold I'm looking for. All right, so you're in the forest, you can't see ahead of yourself, you're sitting at some point A, and there's 3 paths you can follow. And you know that if you follow the correct set of paths, you'll eventually get to this pot of gold. And the question is, how can you make sure that you've taken every possible sequence of paths so that eventually you'll find the one that leads to whatever your goal is? So this is like maze running. Except, like I say, I can't draw mazes. But basically, when you run a maze, you get to a point and you have to choose, should I turn left, should I go straight, or should I turn right?
Is this similar to what we did in 215, the mapping?
Yes. So there's graph theory kicking in here. And Dijkstra. You could build Dijkstra on top of this. All right, so we're starting at point A. Well, here's a way to start enumerating all the possible paths. Start off at point A, and let's just take the first path, 1. Okay, I'm going to push that on my stack. So my stack is going to look like this, and it's going to grow in this direction. And you want to be comfortable drawing stacks either from the bottom of your page to the top or from the top to the bottom, right? Don't get addicted to one. So in this case, our stack's going to grow in the downward direction. So we start off, we put A1 on the stack. And we walk along this path, and we come to a point B, and we have to make a decision. So let's just always pick the first path. So let's take path B1. So we'll push B1 onto our stack, and we'll follow that road, and we get to a dead end. Okay, at this point, pop the last thing that was on your stack, and it was city B, and we went down path 1. Let's increment that 1. Let's go down B2. So let's push B2 onto the stack and follow road 2. And we come to a new junction F. So let's take path 1. So we'll push F1 onto our stack, and that takes us to a dead end. We'll come back, we'll pop that off, we'll increment 1, we'll go down F2, that takes us to a dead end. Okay, we come back, we'll pop off the F2, and if we were to increment that, it would say, let's take road 3, but there is no road 3. So what do? We pop again, and we go back to B, and we went down B2, and if there was a path 3, let's throw a little path 3 in here, we'd say, let's go down B3, so we'd push a B3 on our stack and follow B3, and that's a dead end. So we come back, pop that off, try to go down B4, it doesn't exist. Come back here, pop this off, we're back to A1. Now let's go down A2. So this stack is keeping track of all the places where we made decisions. Right, so we started off here. We need to know at some point that when we come back here, our next path should be 2. And we came out here and we went down path 2. We need to know that when we come back, we should go down road 3. So by using a stack, we can save each of those decision points. And whenever we come back to that same point, we can say, okay, what's the next road we should try? And eventually, you'll either run out of, right, if you don't find what you're looking for, we might have gone down A3, and eventually we come back, we pop off A3, we increment that and say, let's go down road 4. There is no road 4. We know that we're done. We've traveled every possible set of connected paths. And so this is the same way you solve a maze. Right? You start at the beginning and you follow through until you get to a point where there's a decision to make, and you sort of put your finger there to remember which way you go, and you pick a direction and you follow it. And if it dead ends, then you come back to the last decision that you made and you go a different way. And if you come back to the last decision you made and there's nowhere left to go, you have to back up one step more. Okay, that's a stack function. That's taking care of keeping track of those things in order. Does that make sense? Now you can also do this using a queue, but we usually do stacks for some reason. That's just kind of how we seem to have learned to process these things. All right, let me show you something else you can do with a stack.
I have a question.
Yes?
Input 15, there were two destination.
Mm-hmm.
Like you mentioned before, the first one was that one, and the other one was
Breadth first with a queue.
yeah.
Yeah.
So is it possible?
Yeah, totally. Yeah, so we'll do queues later. But the other option here is go down road 1, go down road 1. That didn't work. So now let's go down road 2 and go down road 1 and road 1. Forget that that's there. That didn't work. Come back to the beginning, go down road 3, road 1. That didn't work. Okay, so what are we going to do? Well, we'll go down road 1 and we'll start going down road 2, right? And if we think of this as sorry, let me do that differently. Start off here, see if your pot of gold's there. If not, see if your pot of gold's there. If not, see if your pot of gold is there. If not, come back to this first place that you checked and go one branch from that. Pot of gold, no. Pot of gold, no. Pot of gold, no. Go back to the second place you checked. Pot of gold, no. Go back to the third. Pot of gold, no.
So in this case, we didn't use that one.
In this place, you'd be using a queue. And we'll go through examples of that later and see why. But a stack is doing what we call depth first search. We're starting at A and we're going as far as we can until we get to an end point. And then we back up just a little bit and keep trying to go. So we're staying very deep in this set of paths. A queue is what we call a breadth first search. We start off by checking all the things that are one edge away from our starting point. And then we check all the things that are 2 edges away from our starting point. And then we'll check all the things that are 3 edges away and so on.
Wouldn't that take longer?
It could take longer, but it's also going to give us a shortest path. So in this case, there's only one path to this pot of gold. But if we had sort of a more general kind of graph, and we'll talk about graph theory later. And maybe we had distances associated with these. And we wanted to find what's the shortest path from here to here. Right? We could do that by saying, well, let's just check all the things that are 1 hop away, and then all the things that are 2 hops away, and then 3 hops, and so on. So it can depend on the nature of the problem.
But since that one's got the weights on each individual edge.
Yeah, with the weights, a straight breadth first wouldn't work.
Yeah, that's why you have to use the Dijkstra.
That's why you have to use something like Dijkstra's algorithm.
Is it possible to do different algorithms at once to find pot of gold, like the queue and then the stacking and then like the Jackson algorithm?
Run them simultaneously, you mean?
Yeah, at the same time.
Sure. If you've got multiple cores, you could run them all at the same time, assuming they're not modifying anything. And then whichever one finds the solution first. Right, so there's a, I may as well mention this. So there was this thing I came up with years ago. It's called Ants at a Picnic. And the idea was you were trying to find a solution to a maze, right, a shortest path to some exit point. So the idea was picture, a big hive of ants, right, or a nest of ants sitting at some starting point, and they're trying to find a picnic basket. Well, if each ant just goes off in every possible direction, right, and we're on some kind of grid, so you can't go diagonally, but you can choose to go left or right or straight. And if each ant follows a different path, and they're all walking at exactly the same pace, whichever one finds the picnic basket first has, by definition, found the shortest path. And so I used this to do some automated routing where there were processors in this grid, and each one simply farmed out 1 hop from where it was. And as soon as somebody reached the destination, they just sort of sent a message back and backtracked through, and that gave you the shortest path. And if you took 101 with me, you've heard me talk about slime molds. Slime molds will solve mazes. We don't really understand how. But they, you put some slime mold at the beginning of a maze, you put some oats at the exit, and the mold grows and it spreads out until it eventually gets to the oats. But once it gets to the oats, it actually contracts itself from all the parts of the path that weren't fruitful, and it ends up with a nice solution to the maize. We don't know how that works. But yeah, if you want more Wikipedia, look up Fusarium computing. That's slime mold computing. It's good stuff.
So in that scenario, since there are like different ways that you can get a short path, since it's on a grid, you can go in every direction, then would it give you all of the solution? Which one would it send first if it's looking for one fastest solution?
You gotta worry about race conditions if they both try to send at the same time, but there was a sequencing, and you could only send a message when your sequence number came up. So whichever one happened to have the lowest ID would be the one. And in practice, right, there were regions of this that were blocked out because it was a defective substrate. And so usually you'd only get one that would find the shortest path. I've got a 130-page report on that work if you're interested. All right, what else can you do with stacks? So when we write equations, we use this usual algebraic notation, right? So this means take 2 and 3, add them together. Take 4 and 2, add them together, and then multiply, right? And with algebraic notation, you got to have parentheses because sometimes we want to do things in a particular order. And without the parentheses, rules of precedence would say take 3 and 4 and multiply those, and then add 2 and then add 2. So we get 16, whereas here we should get 5 times 6, which should be 30. Well, this is algebraic notation. There's a different way to represent equations, and this is something called postfix. It's also called reverse Polish notation, RPN. And old Hewlett-Packard calculators used to use RPN for inputting things you wanted to calculate, which was really cool. It's a weird system at first, but eventually it starts to feel very natural. So here's how I would write this expression in postfix. I would say start with a 2, and then a 3, and add them together. And then take a 2, take a 4 and a 2, and add them together, and then multiply. So you need some kind of enter key, so you know this is 2 and a 3 as opposed to 23, right? But I'll just use single digits for now. So this says take 2 and 3, add them together, take 4 and 2, add those together, and then multiply. And this is a fairly comfortable way to write expressions once you're familiar with it. This is what we do in school, this is what we do in algebra, so it's the one we encounter most. But this is actually not as weird as it might seem at first. And so HP calculators use this. Other kinds of systems use this notation. So one of the nice things about this is it's really easy to evaluate an expression written in postfix. Algebraic notation can be cumbersome to evaluate because you've got parentheses. Don't get caught up on the digits. You got enters and stuff, so or something. So on a calculator, you would actually say 2 enter, 3 enter, plus. So if you want to add 15 and 30, you'd say 15 enter, 30 enter, and then you hit the plus key, and it would give you 45. Then you could say 5 and star, and it would multiply 45 by 5, and it would give you 225 or whatever. So this turns out to be really easy to evaluate in a computer. And we do this using a stack. So here's the algorithm. So if it's an operand, push it on the stack. If it's an operator, pop, pop, operate, and push. All right, so what does this mean? So our stack's going to grow in this direction. So we get an operand 2, we push that on the stack. We get an operand 3, we push that on the stack. We get to an operator plus. So pop off the last two things on the stack, that's a 2 and a 3, add them together. 2 plus 3 equals 5, push that on your stack. Here's a 4, push that on your stack. Here's a 2, push that on a stack. Here's an operator plus. Pop off the last two things on the stack. Apply the operator, 4 plus 2 equals 6, push that on the stack. Here's a star, that's an operator. Pop the last two things off the stack. Apply the operator, push it on the stack. There's nothing left in the string. There should be exactly one thing on the stack. That's the value of the expression.
How does it like, so there's like a plus after those two, but you already popped them off, right? So how does it know the value of those? Since you delete them, right, when you pop them?
Well, you save them somewhere so that you can add them. So I mean, this would be something like, op1 equals pop, op2 equals pop, push op1, operator pop2, op2, or whatever. It's a level above pseudocode. All right, and this works for any postfix notation, no matter how complex. Right? So if you had an expression like I think that works. So 4, 2, 3, plus, plus, 6, 3, plus times. Right? So push a 4, push a 2, push a 3. When you get to the plus, pop off the last two, add them, push that on your stack, so you get a 5. You get to the next plus, pop off the top 2, add them, push that on your stack, so your stack has a 9. There's a 6. There's a 3. There's a plus, pop off the 6 and 3, add them, push that on the stack as a 9. Multiply, pop off the 9 and 9, multiply them. That's an 81. Push that on the stack. There's the end of your expression. Right? In algebraic notation, this was the formula. So it'll turn out we can use a binary tree, which is our subject after stacks and queues. We can use a binary tree to convert from this notation to this notation. And then we can use a stack to evaluate things in this postfix notation. So that's another example of stack usage. All right, so tomorrow I want to talk about implementation of stacks. And we'll look at least 2 different ways, but also a lot of variations on those 2 ways. And your third programming assignment, you'll be implementing stacks and queues. So we're moving towards that.